All right, so I'm just going to pick back up where we started from past the last exam. So we started with benzene aromatic compounds. So benzene is like the parent of all aromatic compounds. It's a 6-membered ring, 6 carbons, 6 hydrogens. You have 3 double bonds. And these double bonds actually form a conjugated pi bond, which just means you have 2 or more pi bonds that overlap all together to form a big giant pi bond. Okay, and that allows all these pi electrons in these double bonds to delocalize and spread out to the entire ring instead of just being caught up in just 2 p orbitals. So because of this spreading out, they're much more stable than regular alkenes with double bonds. Their stability is more comparable to alkanes instead of alkenes. So you can write this a few different ways. You can see with the 3 double bonds here, but we know that's not actually the case because these pi electrons can delocalize to all of the p orbitals in this entire ring. So this is how I normally draw it. If you have to draw a mechanism, you'll have to use this because you have to use the double bonds. But in any other case, you can use this. This is a bit more accurate because it shows that these pi electrons are delocalized to that entire ring. So the bonding in benzene, these are the unhybridized p orbitals. And all of these carbons are sp2 hybridized. Okay, and in regular double bonds, you just have pi electrons shared between these 2 orbitals here, above and below. But because it's a conjugated pi bond system, all of these pi electrons can spread to the whole ring. So this bond here, this bond here is formed from sp2 to sp2 orbitals, and then you also have the pi bonds with the 2p to 2p orbitals. Make sense? All right. So this gives rise to aromaticity, which is just an unusual stability of certain types of compounds that are more comparable to alkanes than alkenes, even though they have double bonds. So this is ruled by Huckel's rule, which says if the compound's pi electrons will fit into the formula 4n plus 2, where n is a whole number, then the compound is aromatic, which means it's going to have that stability like benzene. So a few examples here. So this is benzene. We already know it's aromatic, but for example's sake. So to count pi electrons, you can either count how many pi bonds you see. So there's 3 pi bonds. Each pi bond has 2 electrons. So that would be 6 pi electrons. Or you can think of it like every carbon contributes 1 pi electron, which is still 6. So if I set 4n plus 2 equal to 6, n is equal to 1, it's a whole number, it's aromatic. So this one, again, you can count the double bonds or you can count the carbons. It says 4 pi electrons. If I set 4n plus 2 equal to 4, that gives me 4n equal to 2, n equal to 1/2. It's not a whole number. That's not aromatic. So that would behave just like a regular alkene. Okay. So the next thing we learned about was EAS reactions, which are electrophilic aromatic substitution. This is going to be a big part of your next test. So we'll spend a lot of time on this. So because aromatic compounds have that whole conjugated pi bond system, they got a lot of electrons, they can give away. They're electron rich, which means they're nucleophilic, which can donate pairs of electrons, and they can react with electrophiles, which will take the electrons. So the general formula for these reactions is that 1 hydrogen on the ring is replaced with an electrophile. The ones we learned about are nitro group, halo groups, or some alkyl group carbon thing. So we can go over those mechanisms. This is nitration, and you do nitration by reacting benzene with nitric acid, and you have to have a sulfuric acid as a catalyst for this. Okay. So if you remember, this is the structure of nitric acid. Okay. And we know this is going to give us nitrobenzene as a product. Okay, so for the majority of these mechanisms, actually all of them, the thing you're reacting with is not electrophilic by itself. So we use like the acid or like the aluminum bromide, aluminum chloride in the next example to make our reactant an electrophile before we can react it with the ring. Okay, because nitric acid by itself is not electrophilic. That's not going to do anything without sulfuric acid as a catalyst. So what we're going to do is we're going to protonate that OH group on nitric acid with a proton that comes from sulfuric acid. Okay. And this oxygen has 2 lone pairs of electrons. It's going to take that hydrogen and make water. Okay. So now that we have water here, this oxygen has a positive charge. It's unstable, meaning that this is now a good leaving group, which means it can come off easily. So this bond is going to break and give me our electrophile that we're actually going to use to put on the ring, and water. Okay, so now that I have something with a positive charge, now I can react with the ring. So now I have an electrophile. Okay. So the arrow is going to come from the double bond of benzene to the nitrogen. And remember, all these carbons have 1 hydrogen, right? So that double bond is going to break. We're going to add the nitro group to one of those carbons. It doesn't matter which one at this point. They're all equivalent. And then this hydrogen was already there, right? And because I broke that double bond, I now formed a positive charge on that carbon now because it only has 3 bonds now. It's connected to that carbon, and then it also has the hydrogen. So to reform the double bond and get rid of that positive charge, this CH bond is going to break, and those bonding electrons are going to go to reform that double bond and neutralize that positive charge. Okay, and that hydrogen just comes off as a proton because that was our catalyst, right? So we consumed it and reformed it in the reaction, and that comes from the sulfuric acid. Any questions on that one?
What does the good leaving group mean?
Oh, did you not go over that yet?
I mean, you went over it, but
okay,
I
so
don't understand it.
A leaving group just means that a bond is weak enough that it can come off easily. So in this case here, this nitrogen-oxygen bond is strong because nitrogen has enough bonds, it has all the bonds it needs. Oxygen has all the bonds it needs, right? So this is stable, this is strong enough. It's not going to break unless you do something to it. It's not going to spontaneously break. But if I protonate like I did here and add an extra bond to that oxygen, oxygen is bivalent, right? It needs 2 bonds to be stable. I just gave it another one, so now it's 3. So now it's going to be unstable. And now this bond can break spontaneously. And this group can leave.
Okay.
Does that make sense?
Yes.
So a good leaving group just means that bond can break spontaneously. And pretty much, and you're going to see this a lot, in the upcoming mechanisms is water as a good leaving group, because it can come off and it can be stable by itself. That makes sense?
Yes. Yeah.
Okay. Any other questions there? Okay. So always pay attention to your catalysts here and make sure you're reforming that. And we get where I get the proton, right? Because it's a strong acid, it associates in water and makes proton. All right. So halogenation. Oh, and all these mechanisms take place through a benzenium cation, which is a type of carbocation, but this is benzenium here. Okay, so halogenation, my product is I'm going to substitute one of the hydrogen on that ring with one of the bromines. And then I'm also going to have HBr as a byproduct here. Okay, so again, Br2 is not electrophilic by itself. It's not going to do anything with the benzene unless we add that aluminum bromide catalyst. Okay.
That's another like acid that we can use.
It's a Lewis acid, yeah. It's not a Bronsted acid, but yes, it acts as an acid essentially. But it's just a catalyst. We're not there yet.
Okay, so those right there you call catalysts. You don't just call them like.
Yeah, it's a catalyst because you use it and remake it in the course of the reaction. Okay, so I have to make my electrophile again. I have my molecular bromine here. And then aluminum bromide. So this bromine is going to connect to this aluminum here. We're going to make this compound, and then this bromine is now going to have a positive charge because halogens are monovalent. I just gave it 2 bonds, so it's going to be unstable. Okay, so now this bromine to bromine bond here is going to break, and this bromine is now going to connect to this aluminum. Okay, does that make sense? Which will then give me an ionic compound with cation, anion. So now that this bromine has a positive charge, now I can use that as an electrophile. We follow that?
Wait, you put the Al to the first. That means the second Br. When you moved it over, it's on the third. It's still connected to the Br3.
So it connects to this one first, then this Br to Br bond breaks, and then this one connects to this one. So this ends up with 4 bromines on it, including that one, and then this is an ionic compound with this positively charged bromine. Does that make sense? Okay. And we'll also use this catalyst again, and when we actually learn the Friedel-Crafts mechanism as well. But the important thing now is that I have positive charge on that bromine, so now it's electrophilic. Now I can react it with the ring. Okay. So the arrow will go from the double bond to the bromine. Which will break that double bond. I'll add the bromine to the ring, and that will form positive charge on that other previously double bonded carbon. And then I still have this anion. Okay, the same thing. Now that carbon-hydrogen bond is going to break, and those bonding electrons go to reform that double bond there, which will give me bromobenzene. And you don't have to show the mechanism steps for this part, but what happens is that hydrogen combines with one of those bromines on that aluminum bromide to give me HBr, and then that will also reform the catalyst. Okay, so these are products, and then you reform the catalyst. Does that make sense?
On the last one, like the double bond went to the bromine, right? Then it,
Mm-hmm.
okay.
Yeah, those electrons from the double bond went to the positively charged bromine and made a bond there, and then it broke the double bond.
Okay.
And then we reformed it with that CH bond. Any other questions there? Yeah, this step is kind of confusing, but you'll get more comfortable with that. We'll do it a lot more. That comes up with the Friedel crafts, like I said. You would be correct. Yeah, it is what it is.
Up there is the negative charge on the aluminum or the bromine?
It's on the aluminum, I
On the
think.
aluminum on that one.
I believe so, yes. That's not super important.
Oh.
I think it lies on the aluminum. I believe so.
I just didn't know because on like the last, on the, like the bottom one, it looks like you put it.
Yeah, I was just saying that this whole like entity is negatively charged.
Oh, okay.
I'm pretty
Okay.
sure it does lie on the aluminum though.
Do we need to?
You need to put the negative charge. It doesn't quite matter where
Okay.
it is. Pretty positive. I think. The most important part is just that positive charge on the bromine there. Any other questions there? Okay. So he said you didn't need to know the mechanism for this yet. I don't remember when we get to this. It might be second semester. I can't remember. But the mechanism is pretty similar to the halogenation one. You're using this aluminum chloride, aluminum bromide catalyst again. But just generally what happens is you're going to replace one of the hydrogens on the ring with whatever alkyl group is connected to this haloalkane. And then you'll form whatever alkane this is, or whatever halo group this is. So you can have, just generally you can have some alkyl group to some halo group with this catalyst, and then you'll form that. It's very, very similar to the halogenation one. All good there? Okay, so.
It's recording, right?
Mhm.
Okay.
Okay, so the next section is about functional groups. And functional groups are just something inorganic or organic on an organic compound that gives it a specific set of characteristics. So, like alcohols behave a certain way, haloalkanes behave a certain way. So, your functional groups could be like a nitro group, like those reactions we just did were functionalization reactions. We're putting a functional group on an organic compound. So we could have like a nitro group, a halo group, hydroxyl group to make an alcohol. Things like that. So amines. This part right here is going to be quite important for you to know. So make note of that. You don't have to write all this down, but the hydrogen bond part is very important. So amines are derived from ammonia, which is this. Nitrogen has a lone pair of electrons. Okay. And then you can have pretty much the same as all organic compounds we learned about. You can have primary, secondary, tertiary, and that depends on how many carbons is connected to the nitrogen. So we have this down here. This is methylamine. This has one carbon on it, so this would be a primary amine. Y'all watch Breaking Bad? That's from Breaking Bad. Anyway, so again, this is the important part. So because you have this nitrogen-hydrogen bond, which is polar, right? So nitrogen is going to be more electronegative than hydrogen. Hydrogen is going to be partially positively charged, and then nitrogen will be partially negatively charged. If you didn't know, this is gamma. That's what we use to show partial. So it can act as both a hydrogen bond donor and acceptor, either with itself or water. So, like in this example here, we have nitrogen here. All these hydrogens are going to be partially positively charged. So this hydrogen that's partially positively charged can be attracted to another molecule of ammonia or amine. That's the nitrogen is partially negatively charged. So there's going to be attraction there. We're just going to hold it together. And same thing here, this is water. So in water, the oxygen is much more electronegative than hydrogen. So the hydrogen will be partially positively charged. Oxygen will be partially negatively charged. So this hydrogen can be attracted to the nitrogen here, or these hydrogens can be attracted to the oxygen here with other water molecules. Okay. So amines are bases. They're both Bronsted bases, which is a proton acceptor, is the definition of that. And then they're also Lewis bases, which just means they can donate electrons to an electrophile. Okay, so they're nucleophiles because of that lone pair of electrons. Okay, so the next one we learned about was alcohols. So alcohols are formed by replacing a hydrogen on an alkane with a hydroxyl group, which is OH. And remember that the OH, for it to be an alcohol, has to be on an sp3 hybrid carbon. Okay, because we learned about phenols today. Phenols are not alcohols. Just watch that. I don't have phenols in this PowerPoint, but we'll go over that later. And again, they can be classified as primary, secondary, tertiary. And this is going to be very important for like dehydration of alcohols and other mechanisms in determining the regiochemistry and everything. So it's a primary alcohol. When you're looking at the classification of alcohols, you're going to be looking at the carbon that's connected to the OH group. This is called your alpha carbon, which is connected to, it's the first carbon connected to the functional group. Okay. So you're looking at how many carbons is connected to that alpha carbon. So this one has one, so this would be a primary alcohol. This alpha carbon has two carbons connected to it, so it's a secondary alcohol. And this one has three. Okay. And then reactions of alcohol, I forgot to put a slide about this, but you have your alkoxide reactions, which is where you have an alcohol reacted with an alkali metal, so like sodium, magnesium, or lithium, not magnesium, lithium. And you form an alkoxide. That's going to be pretty important too. We're good there? Any questions? Okay. So dehydration of alcohols. I wasn't on class on Monday. I had to run the college fair. Did you go over the difference between the mechanisms of like primary and then secondary and tertiary for dehydration? Good. So this is a tertiary alcohol, right? Because this carbon that's connected to the OH has 3 carbons connected to it. Okay. So this OH group, as it is not a good leaving group, right? It can't come off spontaneously. So in these reactions for dehydration, you have to have an acid and you also have to heat. And depending on the classification of the alcohol, you either have to heat more or less. So I want this OH group off, but I can't take it off just yet. So I'm going to protonate with the sulfuric acid. Okay, just like I did on the other mechanism to make water. Which forms a positive charge on that oxygen. So now this is unstable, now this can come off. So the CO bond is going to break. I'm going to form positive charge on that carbon now because it only has 3 bonds. And then I also lost water. Okay. And this is a tertiary carbocation, which means it can actually be formed. Okay. So that step can actually happen. So now, to form the double bond, to get rid of that positive charge, I'm going to break this CH bond, one of the CH bonds, it doesn't matter which one, out of any of the carbons. And those bonding electrons are going to go to form a double bond on that carbon and neutralize that positive charge. And that hydrogen comes off as a proton, which reforms my catalyst from sulfuric acid. Does that make sense? Was that a no?
That's the only thing that's easy to read.
Yeah, these ones, the ones with alcohols aren't bad. So this is like the opposite of the reactions with alkanes where you add water and make an alcohol, right? It's just the opposite of that. Like the Markov-Nikov stuff, it's the opposite.
Wait, so the one you just went over is the opposite of this?
No. The ones where you have like this and you can add water and that would give you an alcohol. It's just the opposite of that. Any questions? All good? Okay, so because that was a tertiary alcohol, I could do it that way and I could actually make the carbocation and do it in 2 steps. However, so I can do that with tertiary and secondary alcohols. But when you have a primary alcohol, you cannot make a carbocation because primary carbocations do not exist. They're too unstable. So what do you do? Let's see. Okay, so it's a primary alcohol. And again, I want that OH group off, but it's not a good leaving group right now, so I'm going to protonate to make it a good leaving group. So I added that hydrogen to the oxygen, formed a positive charge. Now it's unstable, now it can come off, but it can't come off because if this came off, it would form a primary carbocation, which can't actually be formed. So what I'm going to do is actually we're going to do this all in one step. Instead of taking off the water, forming a carbocation, and then taking the hydrogen, forming the double bond, we're going to do it all in one step to prevent that primary carbocation from being completely formed, okay? So this CH bond will break, form a double bond here, and at the same time, now that water will come off. Okay, so that prevents me from having an unstable carbocation forming. Okay, so this one just happens in one step instead of two.
So you wouldn't show the work for the OSO3 part?
You can if you want. It's the same thing. And so that's the way he does it.
So if we did do that, if we did or did not do that, we'll take points off. Okay.
No, I'll draw it out like that.
Because that's how I
So
learned
you
it.
can
It was
see it's the same
put in
thing.
the O.
Yeah, it's the same thing. So instead of you could just using the proton, you can use the whole sulfuric acid. Which would make an anion, okay? And then the way he does it is
He
then,
types up one
Yeah.
of the H's.
right.
Okay.
It's the same thing happening. You can use this if you want. And you can also use that anion to show the last mechanism too, if you would like. But it gives you the same thing. That's real messy, but
I understand.
don't get me. What's wrong?
No, I like the H plus. It's just assumed that all the rest of the stuff happens.
Yeah, I mean, either way should be fine. I guess the only reason he does it in this one is to show what's taking this hydrogen when this happens all in one step. But it's up to you.
It's not new, I'm just tired. I promise, it's been a long day.
Right here, yeah. Okay. Any other questions? Alrighty, my friends.
Just
Hmm.
basically when you do the H plus part, it's just assumed that it dissociates from in water. The acid
Yeah.
dissociates in water, and that's where we get it from, right?
Yeah, because
Okay.
I mean, when you think about it, you won't always use sulfuric acid. You could use another acid.
But it's
He'll
just the proton.
normally always give you sulfuric acid, but I don't know. It means the same thing.
But it's just the proton associates in water.
Yeah, the proton
Goes
is
there.
what's actually the catalyst, right? It's not the whole acid that's the catalyst. It's just the proton, because that's all you're adding to the OH.
Would we say like blah 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 dissolves it in sulfuric acid, or would we just assume you know it?
He would give you sulfuric acid, I'm assuming. I don't remember exactly what he asked, but he would probably just give you this and ask for the mechanism and the product.
Okay.
Yeah. Any other questions?